Hi, I'm Robert Bolaños. Here I have the Siglent digital storage oscilloscope. It is model SDS2354X HD. It's a 350 megahertz oscilloscope, and it has a sample rate of 2 gigasamples per second. The other noted feature is that it's 12-bit vertical resolution on the vertical, which is very, very good. And it has one of the features that I'm going to demonstrate is the Bode Plot. So I'll be demonstrating that. Now, what I'm doing, or what you see on the plot right here, is actually this breadboard of a power supply that I'm breadboarding. It's a little breadboard board able to wind different types of transformers, and I can plug them in and check performance. Anyway, I have the output. In this case, it's 12 volts, and that would be the blue plot. And you can see the voltage right there. It says 12 volts. And then the green line is the current of the electronic load. I'm also showing the electronic load by Siglent. It's a SDL1020X. It's a 200 watt electronic load, and I'm going to be demonstrating some of the nice features of this electronic load. Now, what I want to do first is I want to do a dynamic load test, which is a important parameter that some power supplies are sometimes tested to. And to do a dynamic loading, you need a electronic load that will be able to switch from one current to the other. So in this case, I'm going to go ahead and program the Siglent 1020. Okay, so I'm going to talk a little bit of the 1020X electronic load by Siglent. It has constant current mode. It has constant voltage mode, constant resistor mode, and constant power mode. And to program it is fairly easy. You have the current ranges. It says to turn it off, so I'm going to go ahead and turn it off. So here in the I range, you can go from 30 to 5. In my case, I'm only programming 700 milliamps, so I'll leave it at that. And then this is the voltage range. You can go from 150 to 36. So those are the two positions, so I'll leave that at 36. And the current is, well, presently it's set at 700 milliamps. You can change that by scrolling over and then moving the little thumb wheel. You can also type it in. And then it's got the slew rate and the fall rate if you do a dynamic or when you turn it on. Okay. So once it is programmed, then all you have to do is press on and it turns on. So let me show how it shows here. So basically that's on, that's off, on and off. Okay. So now we're going to go ahead and do a dynamic programming for a dynamic load, which is very intuitive, and that's why I like this Siglent electronic load. You press Shift Dynamic, and mind you, I didn't even have to look at the instruction manual. This is fairly intuitive. Just by fooling around, you can figure out how to use it. So you have the first of 3 pages. This is the function, constant current, you can pick between the four. And then once you are in the dynamic loading, do you want it in a continuous dynamic load or pulse mode or toggle? Next is the range of the current. In this case, I'm going to leave it at 5. And it has the voltage range. I'll leave it at 36. So then you go to the second page, and then this is what's really neat, in that you can program now level A. Level A is this bottom portion. So in this case, I have 400 milliamps for that level. And then level B is this top level. In the top level, I'm going to have a higher current, so in this case it's 700 milliamps. And then you can program the width of this period, which is the down period. In this case, I'm letting it or setting it to be 100 milliseconds, and then B 100 milliseconds, which is this top portion. Then you go to the third page, and this is the slew rate, which is the slope of the leading and the slope of the falling edge. So I'll leave that as the default, which is the fastest. And then once it's programmed, once you have that, then all you have to do is press the on button, and it says dynamic load. So now let's take a look. In this case, I've set the probe or channel 3 to AC coupling. So you can go DC. If you go to DC, then it's off the scale or off. So with AC, you're only looking at the delta change. Now in this case, okay, so once you switch your dynamic load on, then you trigger it under normal. If you leave it in auto, it might you might get some skipping. So under the normal, it works much better. I can increase this a little bit, and I'll bring this down, and then I can set the trigger right there. That way it'll give me a much stable plot. And here you have the dynamic load of the power supply. Now if you notice, this is 300, I'm sorry, this is 400 milliamps, and then this is 700 milliamps. So when you have a demand in current, in other words, the electronic is actually sinking the DC voltage, or the 12 volts actually sags, and then it takes time for the error amp to sense that it's below voltage, and then once it you see this little minimum, then the control then increases the duty cycle to increase it, and the voltage comes up, and then it overshoots and then undershoots a little bit, and then it settles down. Okay, so typically this will signify, it has maybe a half a ring, you can say that. So this signifies that you have a low bandwidth in your control loop. Okay, so one of the things that we want to know is how much of a drop do we have. So we can press menu. So then we have this cursors. And we can put the cursor about so. Okay, so here you can set that the delta Y or the delta voltage is actually about 2.53 volts. So that's the difference between this point and this point. Now on a 12 volt, that's a huge. So you're dropping down to almost 9.5 volts, and then it recovers. So what can you do this to what? So what can you do to improve this response? Well, one of the things that you can do is you can increase the gain of the loop, or actually not the gain, but the bandwidth of your loop. So in this case, let's go ahead and we can explain what I'm going to do here. On a control loops for the error amp, you usually have a integrator capacitor across the integrator op amp. In this case, this is my integrator cap. And usually this integrator cap will have a resistor. In this case, I'm using a potentiometer in series with the integrator cap. So this would be my integrator resistor. So right now I have it at its lowest resistance. And I'm going to start increasing the bandwidth, or increasing the resistance, and by increasing the resistance I increase the bandwidth. So now let's take a look how. So now we're going to see how increasing the integrator resistor, how it affects. And if you notice, it's getting smaller and smaller and smaller. And I'll continue to increase this to its maximum. And mind you, this is a 20 turn potentiometer. And I think I reached the maximum. I can hear it click. So now I can go ahead and increase the vertical. So then I can bring the cursor back up. This up here. Okay, so let's say I'll put this in the middle of that, and then I'll put that in the middle of right there. So I'm getting about 67 or 69.2 millivolt delta. So now this is much better. It's a much faster control loop. Okay. Now this was done by increasing the bandwidth and the error amp. So let's go back and set this back to where it was before, and we're going to see this is in the time domain. So now let's go back and we can actually use the Bode function of the scope, which allows us to see in the time domain, the frequency domain. So this is going back to time domain, and this is the bandwidth again. Let's go back and measure the loop, or not the loop, but the drop. Again, it's about 2.5, 2.6, 2.4. Okay, so that's a drop. So now we're going to do a Bode plot. And to do a Bode plot, and the back, there is a cable or a connection for where you can connect your injection transformer. In this case, I'm using the Picotest J2101A injection transformer. It's a 1-to-1, and I connect the signal coming from the generator. I'm connecting the output, and I'm injecting the signal between these 2 points. These are my injection points. And I have 2 scope probes here. This is measuring the voltage. This is channel 3. Channel 1 and 2 are connected here, channel 1 and 2. So this will do my Bode plot, which is the frequency domain, and then this is the output voltage, and this is the current. That's your time domain. Okay? So now we're going to do a Bode plot, and theoretically, the voltage or the bandwidth of the loop should be very low. And the way to get to the Bode is, oh, hang on. So before we do that, one of the important thing is, right now we're in dynamic loading, and you can't do a Bode plot. You have to go back to continuous constant current. So I press constant current, press, and now it's in constant current. Then I can go ahead and press this to auto. Okay. So now I can go ahead and go to analysis, and then go to Bode. Okay, so now we have to configure this properly. Now I'm going to go ahead and explain this. This is the device input. That would be channel 1. Here's the other DUT out. So input, output, so it's channel 1, channel 2. And then you go to sweep type, and it says variable type. When they're talking about the sweep, they're talking about the injection voltage. In this case, you can do a simple. When you select simple, the frequency mode will be in decades. You can also do linear. And when you do a decade, then you have the frequency start 10 hertz and stop 100 kilohertz. The number of points per decade is 5. And then this amplitude is actually the injection voltage that you can be putting in. And then you can also put a offset voltage. In this case, we're going to set it to 0. And the amplitude units is in dB volts. And of course, the load, which is the injection resistor, we're going to set it to 50. Now, in this case, when we do a simple, the amplitude is going to be 35 dB volts. And it's going to be constant throughout the frequency range of 10 to 100 kilohertz. But typically, you want to do a variable voltage or amplitude. So to implement that, you go vary level, and then this changes. So now this stays the same. This tells you this is profile A, I believe. I believe I can save it. It's a profile A. Let's see what else. Okay, so you can, I believe you can save different settings. So this would be the frequency mode. It's going to be decade. The points is 10 points per decade. The offset, I'm going to leave it to 0. And the amplitude unit, that's the how much voltage, peak to peak. And of course the load. And then you have this little Bode plot, and it shows the frequency and the amplitude. So this is the frequency, this is the amplitude, and this tells the oscilloscope that at 10 hertz output 200 millivolts, and then at 100 output 100 millivolts, and then once you get to 1K and above, set this to 50 millivolts. And the way you make this is with this editor. So in this editor, you put the number of points. You can put more points here, but in this case, what I did is I just put five points, and I started from 10, 100, 1K, 10K, and 100K. And then here are the amplitudes that I chose. Like I said, 10 hertz is 200 millivolts, or peak to peak. 100 millivolts peak to peak, and so on. So it plots these points in this configuration. So now we can go ahead and close that. You can close that, and now once I am connected, I can press operation. And it should start plotting the frequency response of the loop. In this case, red is the amplitude, the green is the phase. So right from the start at 10 hertz, you're about 30, a little bit above 30 dBs. And it has a downward projection to start with. And what it's doing is it's doing 5 points per decade. And I believe it's probably doing a FTT to measure the ejection signal that the wave generator is outputting. And here it's approaching the 0 dB. So this is the bandwidth. And we'll continue. And then this is the phase. And where the gain crosses the 0 dB, above that, that would be the phase margin. And if you notice, the phase margin is close to 45 degrees. Okay, so that's the bare minimum. Okay. Now, you can also use, I believe, you can use the cursor. Okay. In this case, I move the cursor to around there. And according to this, it says that a crossover is 194 hertz approximately. So that's the bandwidth. Okay. So now if you notice, it's doing a second. I set it in continuous. You can do single, but in this case I'm doing it continuous. So now what I'm going to do is, as it's sweeping, I'm going to go ahead and increase the resistor again, the integrator resistor. And I'm going to turn it clockwise, which means that I'm increasing the resistor. So I'm increasing the bandwidth. And I can hear the resistor clicking, so it's a maximum. So now notice that the plot has changed quite a bit. So now, instead of crossing at approximately 200 hertz, it's crossing at a much higher frequency. And because it has such a higher bandwidth, the control loop is fast enough and it's able to control and adjust out that dropout. So now here it's restarting again, and it's replotting, and then should let it finish. Now, for a scope to have this feature is it's a big deal in that you're able to do your transient analysis using the scope, and then you can actually check the loop response using the Bode Plot. That's a powerful combination of being able to do that on the scope. And I believe because of the 12 volts or the 12-bit resolution and the very low noise capability of the front end, you might be able to do some good or very sensitive to filtering out noise. So there you have it. So now we can measure the where it crosses the 0 dB, and as I place this close to the 0 dB, it looks like, according to this, it's about 18, it's about 17, 18. In this case, it says 17.7 kilohertz. So here's the bandwidth. So we went from 200 all the way to 17 kilohertz, which is pretty good. Now we're going to go ahead and take a look at an equation that will help you set the frequency or the bandwidth depending on the delta voltage that is required. Okay, so now let's take a look at this equation. Okay, this equation is was derived or is in the Vache Vorporian book that he wrote, and this is a pretty nice equation. So basically, he says that the crossover frequency is actually the bandwidth of the loop. And he gets this equation, which we all know, 1 over 2 pi RL times CL, okay, which is the load resistance and your capacitive load or capacitor, output capacitor. And then he goes on to express that voltage is really volts, the resistance is actually volts divided by current. So then he subs this equation, the delta V, delta I, into the equation, and you get this form of the equation. And now when you solve for delta V is now the voltage droop, okay? And this delta I is the dynamic loading that we're putting. This is where we're setting the electronic load, the EL, electronic load. So here's the definition. So in this case, we set the delta current to 300 amps or 300 milliamps. And here's the equation that he gives in this book. And if you look at this equation, then to minimize the delta voltage, which is your droop or the voltage drop, then by looking at the equation, you have control over the bandwidth and you have control over the capacitance. So basically, if you want to make delta V small, then you have to make the bandwidth higher, or you can add more capacitors on your power supply. So here is some of the data. So this was at a bandwidth that we first measured. We measured 194 hertz, and here's my delta. And the capacitor that I'm using in my power supply is 47 microfarads. So I come out with 4.56 volts, but I measured 2.5. Now, mind you, this is an approximation, okay? Okay. So then the second measurement, we got a bandwidth close to 17 kilohertz, and when I plug in the numbers, I get 66 millivolts. And I'm sorry, it's not 66, 59. 59. Yep, 59.7. And we measured 66 millivolts. So this equation kind of gives you a feel of what type of bandwidth you need for a given delta V requirement. Okay, so I gave a demonstration how to use the Siglent uh, scope, which is a really nice scope. It has a lot of other features that I'd like to explore. I believe you can measure the switching losses on the transistor as a analyze menu for that. It has 12 bits of vertical resolution. It has a large memory. I believe it can go up to 200 megs of space. And the bandwidth is 350 megahertz, which is pretty good. And that FRA feature that it has for power supplies is a very indispensable piece of equipment. In addition, the electronic load is very intuitive. It's easy to operate. I didn't even look at the owner's manual. I just started playing with it, and it was just that easy that I was able to operate it in no time. So those are the two pieces of equipment, and they're very good equipment, and I recommend them. If you found this tutorial product review, uh, please subscribe, share, and give a thumbs up. And I'd like to thank Jason Chonko for giving me the opportunity to play with the oscilloscope and with the electronic load. So big thanks to Jason Chonko. Thank you for watching.